We're given a metal which is made of silver and has a mass of 40 grams, initial temperature of 220 degrees Celsius. We're asked to calculate the specific heat experimentally. The accepted specific heat is 0.234 joules per gram Kelvin. And as you can see here, that unit is the same as joules per gram degrees Celsius. You can find this value from the simulation. This metal is dropped in a container that contains liquid water, and it has a mass of 30 grams, initial temperature of 20 degrees Celsius. The specific heat of water is a constant, and it's 4.18 joules per gram Kelvin. You can see that on your simulation. When the two are allowed to interact, the final temperature, which is the equilibrium temperature reached, is 33.89 degrees Celsius. Here is our working equation. The heat Q lost by the metal plus the heat Q gained by the water is equal to 0, where Q stands for heat and it's equivalent to the product of mass M times specific heat C times delta T, which is a change in temperature, which is final temperature minus initial temperature. So if you were to represent the statement, the equation in words above, it will end up looking like this. MC delta T of the metal plus MC delta T of water equals 0. So that means the total heat exchange in your system, which is isolated, is 0. When we substitute our values, we have 40 grams times C times 33.89 degrees Celsius minus 220 degrees Celsius. That whole quantity is added by the product of 30 grams, 4.18 joules per gram degree Celsius, and the difference between 33.89 degrees Celsius and 20 degrees Celsius. That's equal to 0. Here we can then calculate for C, and it ends up as 0.233975. This is our experimental value for the specific heat of silver. The other question is to find the percentage error, and that would be the absolute value of the experimental value minus accepted value divided by accepted, the whole thing multiplied by 100. So we can see here that we're very close to the accepted value because our percentage error is only 0.0107%.